Okay, thank you very much. Yeah, I'm very much enjoying this meeting, so thanks very much for inviting me and to the organisers. My name's Roger Colbeck from the University of York, and I'm part of this recently started integrated quantum networks hub in the UK, which has a lot of partners, which I won't go through now. What am I going to try and tell you about today? I'm going to try to make the case for device independence. Okay, so device independence is a more secure form of cryptography that even more secure than quantum, where you try to remove hardware assumptions. So you don't want to have to trust what your device is doing when you're doing the cryptographic protocol. So I'm going to try to explain how and why that's possible and why this is extremely useful. So just very basically, probably everyone knows this. This is a basic setup for usual classical cryptography. We have some user in a trusted lab. Alice wants to talk to Bob. Alice and Bob have identical labs. They have some trusted classical computer. They have a trusted private random string. But anything they want to send to each other goes over this authenticated classical channel that the eavesdropper can listen in on. And that means we can't have unconditional security, where Eve is only limited by the laws of physics. Or we can't prove hardness of hacking in general. And with the event of quantum algorithms for many protocols, we even know that quantum computers can break them. So then we go on to a quantum setup. What changes? Well, now inside the labs, there's some trusted quantum device. This is the usual quantum setup. There's now an insecure quantum channel that connects Alice to Bob. And this removes these classical drawbacks that I've mentioned before. So now we can have what's typically sold as provable security. Okay, and actually for the next few slides, I just want to ask, really, what does this provable security actually mean? Okay, so what does it mean when we say we really have provable security? Well, a security proof should be some kind of mathematical theorem. You take a protocol that you're going to run, you have some assumptions, so I've sort of encoded some assumptions in this diagram. This kind of hash basically means the lab is secure, what you're doing is secure, there's some trusted classical computer, there's some trusted private randomness. So you take your protocol, you take your assumptions, and together you prove that if you run those protocol under these assumptions, you get security according to some hopefully correct or useful security definition. Okay, so this is going to be at a high level. So, for example, probably the most famous quantum cryptographic protocol is BB84. And in BB84, what the protocol assumes, or what the protocol says, is Alice needs to send one of these four quantum states, so either the 0 state, the 1 state, the plus state, or the minus state. Bob needs to measure either in the 0-1 basis or the plus-minus basis. And if you run the BB84 protocol, assuming that you can do this perfectly, you can prove security. Okay, so that's what it means that we have security based. Well, it's based on the law of physics, because what we prove is that provided an eavesdropper is only limited by quantum mechanics, they don't have any computational limitations, then if you run the protocol correctly, the eavesdropper cannot get any information about the key. The key is perfectly secure, or epsilon close, as arbitrarily close to perfectly secure as you want. Okay, what's the problem with this, or what could be the problem with this? Well, the problem is we have this kind of theoretical device, which is this thing that we write in the protocol. We either create 0-1 plus or minus, and we do, say, measurements like this. But actually, then we go out and try and build this device. And when we go out and try and build this device, it's only, I've put this approximation symbol, but this, we hope, is close to what the real device is doing. But actually, this could be quite different. And if, when you go out and build a real device, it's not the same as your theory device that you've done the security proof for, then although you've got this nice security proof for the real device, it might not actually apply in the real world. Okay, so this is kind of a problem. Okay, and so to summarize what is the problem, it's basically impossible to build devices that create states and measure perfectly as we'd want in our ideal protocol. Of course, you could say, well, okay, fair enough. Let's take what we actually can build and let's try and model it. Okay, so this is what you might try and do in an assurance process. So if I'm a manufacturer of some quantum devices, I might want to get a certificate that these devices really do what they say they do. Or even just as the manufacturer myself, I might want to know, what do my devices really do, right? If I'm trying to sell you a cryptographic protocol, right, the last thing I want is to be embarrassed by the fact that someone comes along and later breaks that. Okay, and how can I make sure that they don't break it? Well, if I have a really, really good model of my device, and I can actually prove not only that, but I need a new security proof that works not with this nice model, but with the realistic model, then I might be on a much stronger footing. But of course, modeling realistic devices is actually extremely difficult and expensive. And there's no such thing as a complete model, right? No matter how much, you try and take a real physical system and you try and model every single detail of it, it's not really possible. And whenever there's a mismatch between the way you've modeled your device and the way it actually operates, in principle, that could be a flaw. Okay? So that's kind of the problem that we're trying to get around. And this is not just a theoretical problem. So this is, there's a publication here. Okay, it's quite an old one. It's not the only one. This is just an example of a quantum hacker. So this is the group of Vadim Makarov, and this is his briefcase that he walks around with all his hacking equipment. But essentially what he can do, or what he has demonstrated, is the ability to break quantum cryptographic schemes, which you say, well, that should be impossible. They're proven, information theoretically secure. But the way he breaks them is that he knows more about the actual device than the way it's modeled in the theory, and so he actually breaks the implementation. Okay, and so when he comes along with his hack, then the people who build the protocol, they can then patch that hack, and you can get into this kind of hack and patch security cycle. But this feels a bit wrong from the way we normally like to sell quantum cryptography, because we don't want to be hacking and patching. We want to really be able to prove security. So a way to break out of this cycle is to try and make weaker assumptions. So the weaker the assumptions you make, the easier it is basically to satisfy this approximation, and you get more security. And the idea of device independence is actually to try and remove all the assumptions on how the quantum devices work, which means you don't need to model them at all, and this gives you probably the strongest level of security you could really hope for. Okay, so what it does is the protocol should actually check the working of the devices as it operates. This means there's no need for a detailed assurance process or detailed modeling. This also protects you against faulty devices, tampering, something going wrong that you don't expect, and it breaks us out of this hack and patch security cycle. So to remind you, here's the usual quantum setup, and all that really changes in the device-independent setup is now this device, all the quantum devices now have this little devil symbol on them, which now means we don't have to trust those anymore. Okay, and if you've not seen this idea before, you think, well, this just seems ridiculous. Like if you have a device and you just have no idea or don't trust what it's doing, how can you possibly hope for something to be secure? So I'm not going to go into too much detail, but I'll just try and present the underlying idea. And the underlying idea is based on Bell's theorem, and it basically says that if you have two devices, so one of these is going to be held by Alice, one of these is going to be held by Bob, and what you do is you make inputs and outputs to these devices, and what Bell's theorem says is that if your input and output statistics, after many rounds, if they violate a Bell inequality, and if you chose your inputs randomly, so the inputs could not be guessed in advance, and if these devices cannot communicate with each other, so this is like what this wall is supposed to represent, then according to Bell's theorem, essentially these devices must be measuring entangled particles. Okay, and what this means is I don't need to open these up, look inside them, see what's going on, do all this kind of fancy theoretical or experimental modeling, all I have to do is check their input-output behavior, make sure I've got good random number generators to choose the inputs, and make sure they cannot communicate. And if I'm happy with those very mild assumptions, relatively easy to check assumptions, then I can be sure that these devices must be making measurements on quantum particles. And in particular, this means that an eavesdropper cannot know A. So this is the high-level idea. Of course, there's much more in a protocol than this, but I don't have time to go into the details. So now I'll just try and move to the summary. So usually you need to model devices in detail in order to actually prove that your real devices actually have security. So it's a bit glib to say security is guaranteed by the laws of physics. It is if your devices really work perfectly, but otherwise you also need to make sure that your model of the devices really matches the real devices well enough. And device modeling is very difficult and expensive. And for companies in the QKD sector, this should really be of a concern because, yeah, you don't want to have this problem of things getting broken. Device independent just removes this problem of the modeling because you can check during the protocol, basically by looking at the input-output behavior only, that the devices are working as well enough as they need to. And okay, I'm sort of I'm trying to sell this to you, so I haven't mentioned the disadvantages, but of course the disadvantage, which I do bring up here, is that we do need entanglement to do this, so it doesn't come for free. So there is an expense, but I think because of the improved security it offers, I mean, this really is something that is worth developing, and I believe it really is the long-term solution to this problem. And yeah, this is something that we're working on, is ways to try to help make this more practical. To make this more practical, we'll need new ideas from both the theory and the experimental point of view. I'm working on the theory side, but together with some experimentalists, we're trying to make this happen. But I'm very happy to discuss this more with anybody here. So, thank you.
So we have time for one question. I go that way. And the device you use to check Bell inequality, is that sorry? And the device you use to check Bell inequality, is that any simpler than the device you don't want to model?
That's the one you don't want to model, yes.
No, the one, this little box that you drew around Alice and Bob's device, that's also a device.
So this thing here is the device. So this like dotted line is kind of another strong wall because, you know, I also want to make sure this device can't like look around my laboratory if I really don't trust it.
But this would be the trusted classical computer.
Yeah, so you have to trust something.
To actually compute the Bell value, I'm using this
Right.
trusted classical computer. Yes.
And is it any safer? Or are you
Well,
just
if you
kicking the
if you don't trust this, do it in your head, work it out on a piece of paper. It's not that hard, right? No, I mean the reason you might want to trust a classical computer more is that it's repeatable. So you can, if you don't trust that company's computer, you buy another company's computer. You can really check classical computations yourself. Whereas for a quantum device, you cannot really check yourself whether it really measured that quantum state or not, because it's not directly repeatable. So I think it is more reasonable. I mean, you have to trust some kind of classical computer anyway, like your brain. but
my question was, do you trust something that you have more reasons to trust than that you?
I think you have much more reason to trust a classical computer because it's much more easy for you to independently check that it's doing what you think it's doing.
If I can just,
when it's someone else's device.
but also it's just something you can genuinely do in your head. You can do it on paper.
Not any more than that thing. It's not.
But I think, you know, you've got trouble with all crypto systems if you don't trust you. So this is like an assumption that everyone makes. Yeah.
Apologies if it's a bit of a naive question, but how come accurate device modeling is so difficult or impossible?
Because what you actually have to do is you have a real physical system, right? So suppose if it's going to be running some kind of quantum protocol, what you would ideally like to do, let's take a very the most simple quantum idea of a random number generator you might imagine if you just study physics. You have a single photon device. You maybe send it through a beam splitter, and you just put 2 detectors to see whether it got reflected or not. And now, what is actually a detector, right? So you'd like your detector to be one of these measurements in the 0-1 basis, but actually it's going to be measuring some kind of complicated POVM. And if you really go into the physics of how it does that, there's some kind of avalanche process where a photon comes in and hits this system, and then there's an avalanche effect that makes it macroscopic, and how do I model all the details of that? So at some level I have to be pragmatic, and I have to say, okay, I'm not going to model microscopically every particle in this system. I'm going to make a kind of broad scale model. And whenever you do that, you're in principle losing something that, someone smarter than me might make a better model of that device, and within that better model of the device, my security proof may not hold. Of course. So yeah, there's never an end to the abstraction level in principle. Of course, you can be confident after a while if enough people have tried to make a better model and failed, and this protocol's been around for a while, you can get more and more confident. But
Okay, so let's thanks Roger again. Move on to the next talk.